Hey guys, welcome back to Life at Home Chemistry Shorts. This is Chris Key. Today we're going to be talking about exceptions to electron configurations. And if you've been learning electron configurations, then you probably have already noticed that there's some exceptions in there that don't seem to follow the same rules that the other atoms do. And we're going to try to provide some explanation for that. You may be the type of person that doesn't really, you just want to learn the facts, and having the additional information might offer some confusion to you or bring some confusion to you. So don't get confused by this. If it's confusing, then just go back to learning the basic rules and memorizing the exceptions. For those of you who really want to know why we have these exceptions,
I'll answer the question. You want answers?
I think I'm entitled.
You want answers?
I want the truth!
all right, welcome back, guys. And today we're going to be talking about electron configurations and why we have exceptions. Now, of course, by now, hopefully you guys have learned the basics of electron configurations. And I've started here with scandium through zinc to kind of illustrate the point here. So as we move across and we add electrons, you guys are, of course, familiar with the Aufbau principle. And the Aufbau principle says in the ground state of any atom or ion, electrons fill orbitals of the lowest available energy before filling higher energy orbitals. Of course, by now you understand that. However, when we take a close look and we start looking across this row, we'll notice very quickly that chromium and copper don't seem to obey the Aufbau principle.
Oh, you're crazy. Am I? Or am I so sane that you just blew your mind? It's impossible. Is it? Or is it so possible that your head is spinning like a top?
We're going to take a look at this today, and hopefully we'll be able to get some answers and some insight into this. To get started with this, let's look back at a couple of principles that I want to expand upon. And the first one being, as we move across the periodic table from left to right, we know as we add protons, the atomic radius gets smaller. So as we move from lithium to beryllium to boron, carbon, nitrogen, on across to neon, as we continue to add protons, the pull of the nucleus is getting stronger and stronger, and it's actually pulling the atomic radius in. And of course, if we add another layer on the outside of that, then it gets larger, but then the process repeats itself. So we know as we move from left to right across the periodic table, the atomic radius gets smaller. And of course, as we move down, the atomic radius gets larger as we add primary levels. The reason for this is the stronger pull from the nucleus is actually drawing in the orbitals. It's drawing them in tighter and closer and to the nucleus, which means there actually would be considered the energy level for those orbitals would be getting lower. Also means it would be harder to pull an electron from those orbitals. Now, I think you guys have already learned this and probably understand this concept by this point, but there's another aspect to this that you may not have learned or have heard. Let's look at the shape of these orbitals. An s orbital is a sphere, and of course, d orbital can have both of these shapes. Most of them are the four balloon shape, but then you also have one d orbital that is this shape that we have in the middle. As the nucleus is acting on these orbitals and pulling them in closer and closer, it is actually acting on the d orbital in a greater manner than it is the s orbital. So what's going to be happening is this d orbital is going to shrink and pull into the nucleus at a higher rate than the s orbital. So it's going to get smaller at a quicker rate. The reason for that has to do with the fact that if you look at the s orbital, it's a sphere, and then you look at the d orbital. If we could do a percentage of the amount of time that the electrons spend close to the nucleus, it's going to spend more time closer to the nucleus with the d orbitals than it would with the s orbitals. So that proximity, or that probability of being found closer to the nucleus, is what causes the d orbitals to contract at a quicker rate than the s orbital. As we add protons, all the orbitals are getting closer and tighter to the nucleus, and all of them are getting slightly lower in potential energy, or at least the electrons in there are going to be at a lower potential energy because they're closer to the nucleus, but it's happening at a slightly faster rate for the d orbital than it is for the s orbital. And we're going to come back to that in just a little bit, but first I want to talk about another principle that you guys have already learned, but I want to expand upon it. Now, I've got a set of 3D orbitals up here for your reference, and so you can take a look at it, and you can see we got 5 electrons, one in each orbital. You guys are familiar with this, and it's referred to as Hund's rule, which states that every orbital in a sublevel is occupied by one electron before any orbital is occupied by two electrons.
Seats take. Take.
Now, you guys know this, but I'm going to expand upon this concept just a little bit. Now, I mean, why is this the case? Why can an electron not go into the orbital with another electron until all the orbitals are at least occupied by one electron? Okay, if we actually wanted to take one of these electrons and place it in and pair it with another electron, we could do that, but you're going to have to add some energy to the system because it actually would take energy. Well, maybe not that much energy, but it would actually take a little bit of energy to take that electron and actually pair it with another electron if there is an empty orbital available that's the same energy level. And we call this energy pairing energy. So basically, now we can get in, there's a lot of debate as to what is the root cause of pairing energy. Some people would say this the innate repulsion of the electrons within the orbital. You know, they're both negative charges, so they're repelling each other, and so it takes a little bit of additional energy to pair those together. Other people would say that there's reduced shielding in this orbital, so the energy level is not quite as low. And we're not going to get into the details of that, but basically you just have to understand that when you put two electrons together, then it's just a slightly higher energy level than if an electron can go into that same sublevel or that same orbital without being paired with another electron. Okay, so to move on and try to pull all this information together so you can understand it and see how this all comes together to explain exceptions, we're going to start moving across that row that I showed you earlier. And we're going to start with scandium. Now, what I've done is I've made a line here at the bottom. It's going to stay in place as we move across the periodic table. And so that'll help you to understand that every one of these, as we add protons, every one of these energy levels is going to pull down just ever so slightly. And you'll be able to see that because we're going to leave this line in a fixed position. On the other hand, we're going to let this line move relative to the 4s orbital. So it'll drop down and stay kind of even with the bottom of the 4s. And so that'll help us to see that the 3D orbital is actually gaining ground. It's actually moving closer to the nucleus at a slightly faster rate than the 4s. And we'll see how that affects the electron filling order as we move across. So now these changes are very subtle, so you might want to back up and watch it again if you miss it. But we're going to move across and we're going to add a proton. And of course, now we'll have titanium. And you'll notice that everything dropped slightly, but the 3D orbital, the d orbitals, actually all of them that are in, we just don't have any field in this particular row, but all of them will drop just a little bit faster than the s orbital. And so it'll actually gain ground and become less, it's a higher energy level than the 4s, but it'll become less more so as we move across. We're going to add another proton, go to vanadium. Now, by the time we get to chromium, you'll notice this is our first exception, and you'll notice that all of a sudden, instead of putting 2 in with a 4s, it fills up this 3D orbital instead. And the reason for that is because now the energy difference between 3D and 4s is close enough that it's actually less than the pairing energy. In other words, it would take a little bit of energy to pair those. They become so close to the same that the pairing energy is actually more than the difference in the energy between the 3D and 4s. Now, of course, when we move and add another electron, you can imagine, I'm sure you can guess what's going to happen. Now, everything has an electron in it, and so it's going to go to the 4s because the 4s is still technically lower. And when we take pairing energy out of the equation because everything already has an electron, it's going to go back to the 4s. And then, of course, as we move on across, we're going to continue to fill just like you would expect it would. But you notice that 3D orbital is getting mighty close to the same energy level as 4s as we continue to pull it down with that increased attraction from the nucleus. And when we get to copper, by that time, the 3D orbital is actually slightly lower than 4s. So now we've actually pulled it down enough that it's actually past the 4s and it's a slightly lower energy level. So it will fill first. And of course, finally, if we want to round out this whole d orbital row here, when we get to zinc, then of course it goes back in the 4s and it fills everything up. So as you can see, two concepts that are controlling what's happening here that you may not have learned before this point. And one is that the d orbitals are being pulled to the nucleus at a higher rate or more aggressively than the 4s orbitals. And two, the pairing energy that is involved factors in 3d and 4s are so close, and this is going to be the same case for all the other d and s orbitals. They're actually close enough in energy that as that d orbital gains on the s orbital, eventually it gets close enough that pairing energy will factor in, and it'll treat them all the same with regards to Hund's rule. Hopefully that was helpful to you, and if it causes you confusion, then if it's easier for you to just memorize the exceptions, then that's up to you. You can do it that way. But if you're the kind of person that really wants to know the in-depth explanation for why things happen, hopefully that will be helpful to you. All right, guys, I hope this was helpful. Don't forget to subscribe and like this video. Hit the bell so you'll know when I'm posting new videos. I try to post a new video every week or so. And if you have any questions, you're welcome to put them in the comments, and I'll try to answer those questions as best I can. And I will see you guys next time.